Hi everyone, today we're going to talk about related rates. Related rates problems involve two or more variables that change at the same time, sometimes at different rates. If we know how the variables are related and how fast one of them is changing, we can figure out how fast the other one is changing as well. This usually involves writing an equation relating the variables and then taking the derivative of the equation. To give you a better view of what I mean by that, let's think about something we all deal with: the price of gas. What happens when gas prices go up? Generally, we find out that a little later, the price of groceries might go up, the price of ride shares go up, the price of traveling in an airplane could go up, and in general, our wallet becomes empty. This graph shows how the cost of gas has affected airlines over many years. You can see from 2011 to 2021 that the cost of gas has been a large percentage of expenditures for airlines worldwide. This up and down expenditure shows us how costs can change over time. This is often why companies have to raise prices. They have to even out the rising costs by increasing their revenue. We know that profit is equal to revenue minus cost. When costs increase, profits often decrease. In this section, we will use implicit differentiation to find derivatives of variables that are connected. Pay special attention to the independent variable. It might be the quantity or the price or time. It's also important to point out that this technique allows us to calculate an increase of more than one unit, meaning we could increase quantity, price, time, etc. by given values, and I'll make sure I point out when we do that. To start, we're going to go back and practice doing implicit differentiation, and notice I've added a third variable this time. So we're looking for dy dt, and x cubed plus y cubed equals 9. We know that dx dt is equal to negative 3 when x is 1 and y is 3. Our equation x cubed plus y cubed equals 9 doesn't involve t at all, but by saying we're finding dy dt, it means that x and y are both changing with respect to t. In the real world, that t would mean time, so we'll kind of think of it as time as we do this problem, and say that maybe if this was movement, that x and y would both be moving as time progressed. So we can take we'll start by taking the derivative. X cubed becomes 3x squared, but because x is dependent on time, we're going to have to write dx dt, plus y cubed becomes 3y squared, also gets a dy dt. 9 is a constant, the derivative is 0. Now we have some values to plug in. So I have 3. We said x was equal to 1. We square it. dx dt was negative 3. Plus, we have 3. Y was equal to 2, we square it, and we're looking for the value of dy dt. 3 times 1 squared times negative 3 gives us negative 9, plus 3 times 2 squared, that gives us 12, dy dt, equals 0. We'll move the 9 to the other side. I have 12 dy dt equals 9. So dy dt is equal to 9 over 12, which we could reduce down to 3 over 4. To help you understand what we're talking about, I graphed x cubed plus y cubed as 9, and then I put on the point 1, 2. We said that x is going to change by 3, so I'm going to move this point 3 over. So think we were at 1 and we're subtracting 3, that's going to put us at negative 2. So I'm getting as close as negative 2 that I can by just moving this point over, and I want you to see what happened to the value of y. Y was at 2, and now we can see it looks like it's about 2.566. We said it was going to go up by 3/4. Remember, the derivative is an approximation of how it's increasing, so we can see that increase. So if I change the value of x by 3, and a negative 3 this time, I can see the value of y increased. This is the first time we've been able to change x by more than 1. We usually say if x increases by 1, what happens to y? This time we changed x by 3, and then we saw what happened to y as a result. Our second one says, assume x equals x of t and y equals y of t. This means x and y are both functions of x, so t is the independent variable and x and y are both dependent on how t changes. This time we want to find dx dt. Given that x squared plus y squared is 25, dy dt is 3 when x is 3 and y is 4. Start by finding the derivative. So x squared becomes 2x dx dt, y squared becomes 2y dy dt, and the derivative of 25 is 0. We're going to plug in all the values that we know. We have 2, x was 3, we're looking for dx dt, plus we have 2, y was 4, and we know dy dt is changing by 3. This gives us 0. We can simplify that. 2 times 3 is 6 dx dt. 2 times 4 times 3 is 24, and that's 0. We can move the 24 to the right. That says 6 dx dt equals negative 24. When we divide by 6, we get dx dt equals negative 4. Now we're ready to try some applications. The demand equation for a certain product is 4p squared plus q squared equals 1600, where p is the price per unit in dollars and q is the number of units demanded. We want to find dq dp, then find the value for dq dp at the point 1624. dq dp means how does the quantity change when the price changes, so at the end we'll do an interpretation of what we found out. Start by finding the derivative. It's important to note that p is our independent variable. That means when I take the derivative of p, I don't have anything else to add, I just do the derivative like I used to. So 4p squared becomes 8p. Q squared is 2q, but quantity is dependent on price, so now we have a dq dp. Derivative of 1600 is 0. Well, we have values, 16 and 24 to put in. I have 8, price was 16, plus 2 times q, which was 24. And then we're still going to find what happened to the quantity when we change the price. 8 times 16 is 128. 2 times 24 is 48. We still have dq dp equals 0. I'm going to move the 128 over to the left, so I have 48. dq dp equals negative 128. Divide by 48, we get negative 2.67. This says if we increase the price, so the price was 16, if we increase the price from 16 to 17, then we expect that the quantity will decrease from 24, and it will decrease by about negative 2.67. So changing the price is going to change the number of items demanded. Next, given the revenue and cost functions, r equals 42x minus 0.5x squared, and c of x is 6x plus 15, where x is the daily production, find the rate of change of profit with respect to time when 25 units are produced, and the rate of change of production is 5 units per day. We want to start by saying, what's the independent variable? And the independent variable this time is time. That's what we're looking for, the rate of change of profit with respect to time. So time is independent. Both the revenue and the cost change with time. The profit will be equal to the revenue, 42x minus 0.5 x squared minus 6x plus 15. That says P is equal to 42 minus 6 gives me 36x minus 0.5x squared minus 15. When I take my derivative, everything changes with respect to time. So every time I take a derivative, I add a dt. Start with P becomes dp dt, so the profit's changing with respect to time. Derivative of 36x is 36, but then I have a dx dt minus 0.5 x squared. The 2 comes down, which makes that a 1, so I have minus x, also gets a dx dt. Derivative of negative 15 is 0. It's time to plug in our values, so we want dp dt is equal to 36 times, go back to the original problem. It says find the rate of change of profit with respect to time when 25 units are produced, that's x, and the rate of change of production is 5 units per day. This is dx dt. So my dx dt is going to be 5. We're going to increase the level of production by 5 units, minus it started at 25. And again, we put the 5 in for the change. Now I have 36 times 5 minus 25 times 5, which says 55. The interpretation then is the profit is going to increase by $55 if we started at a level of 25 units and decide to increase it by 5 units per day. So we're going from 25 up to 30, which means the profit will go up by 55. Next, we have a product sells by word of mouth. The company that produces the product has noticed that revenue from sales is given by R of t equals 3 times the square root of x, where x is the number of units produced and sold. If the revenue is changing at a rate of $800 per month, how fast is the rate of sales changing when 1,700 units have been made and sold? When we're done, we're going to round the answer to the nearest dollar per month. Start with the product sells by word of mouth. I think that happens all the time. We share if we like something, we put it maybe on social media, so this is a good way to look at something and saying that you don't always have to spend money. It might be just people share what they like. So we're looking at that changes by time. Day after day, people share things, and we can see that increase in revenue because people have talked. So when we're looking at this R of t, notice there's a t and there's also an x. Time is the independent variable again. Let's go through and take a derivative. Before I take the derivative, I'm going to rewrite the revenue. I'm going to write that r is equal to 3 times x to the 1/2 power. Easier to take the derivative if I can see the powers. The derivative is with respect to time, so we're going to write dr dt equals, the 1/2 comes down, I have 3/2, x to the negative 1/2. Don't forget your dx dt. Let's go back to the problem and see what we know. It says the revenue is changing at a rate of $800 per month. That's dr dt, so we can put 800 equals 3/2. Then it says 1,700 units have been made and sold. So x is 1,700, and then I have my dx dt. So don't forget to put your power in there. We still have our negative 1/2 power. We want to solve for dx dt. Definitely use your calculator. You could put all of this in at once. I have 800 equals 3/2, 1,700 to the negative 1/2. So what I'm going to put in my calculator, and I will show you what it looks like, is I'll have 800 over 3/2 times 1,700 to the negative 1/2. At the end, we said we're going to round to the nearest dollar per month if that's necessary. All right, so I'm going to Desmos, and I'm putting in 800 divided by 3/2. Push your arrow over so it's no longer in the denominator. I'm going to put parentheses, 1,700, close parentheses, to the exponent of negative, I'm going to put 0.5, but you could do a fraction also. What I see is $21,989.89667, but we said let's round it to the nearest whole dollar, so I have 21,990. All right, what does that tell us? What is our interpretation? It says if we want to continue having our revenue change at a rate of $800 per month, then we're going to have to continue making more and more items. So if we're currently making 1,700 units, we're going to have to increase that by 21,990 to keep track with this raising revenue that we're hoping to get. A company knows the unit cost C and the unit revenue R from the production and sale of X units are related by C equals R squared over 172,000 plus 6,899. Find the rate of change of revenue per unit when the cost per unit is changing by $9 and the revenue is 1,000. So start with, what is our independent variable? Well, when you read through, you keep hearing this unit, right? Unit keeps being said. That says the unit is our independent variable. We can call it X because we usually use X as the number of units that we sell. This says we're trying to go through and find how is cost changing, so dc dx equals R squared becomes 2R. You can just keep the 172,000 in the denominator because it's really just a coefficient. So I brought the 2 down, I left the 172,000 alone. You don't want to forget to do dr dx because the revenue is changing with the amount of units being made. 6,899, that goes away. So we're trying to find the rate of change of revenue. This is the one we don't know, is dr dx. When the cost per unit is changing by 9, so the cost per unit is 9, leave the 2, and then we know the revenue is currently 1,000, so we'll put in 1,000, and then we have our 172,000, and what we're solving for, dr dx. Well, it's nice that we have this 1,000 over the 172,000. You can cancel out the zeros. That'll make it a little bit easier. If you wanted to, you could reduce the 2 over 172. Not completely necessary, but we do know we need to bring this 2 over 172 over. You can think when you divide by a fraction, you multiply by a reciprocal, if that helps you. If you're just going to put it in your calculator, it's fine just like that. Remember to use parentheses. 9 over 2 divided by 172 says dr dx is 774. I think this is great news. Cost is only changing by $9, but the revenue is changing by $774. If revenue is changing a lot and cost is changing a little, that says profit is doing great. Our last one, the number of custom bracelets X an online retailer is willing to sell per week at a price P is given by X equals 0.75 P squared minus 2P plus 30. Find dP dx, then evaluate at the point 1085 and interpret your results. Step number 1, what's the independent variable? It's X. So when I take the derivative of X, I don't have to write the dx with it. Our X to start, derivative is 1. 1 is equal to the derivative of 0.75 p squared. The 2 comes down. 2 times 0.75 is 1.5 p. Then I have dp dx. Minus 2p is 2 dp dx. Plus 30, derivative is 0. We only have one thing we don't know. We don't know dp dx. In our ordered pair, the first number is p, the second number is x, the quantity. So we know that this is our p. We have 1 equals 1.5 times p, which was 10, dp dx we're looking for, minus 2 dp dx. 1.5 times 10 is 15, so I have 1 equals 15 dp dx minus 2 dp dx. 15 minus 2 is 13. I can divide, I get 1 over 13 is dp dx. What does this say? It says, how is the price going to change when the quantity changes? Our interpretation is the price will increase 1 over 13, which is roughly about 8 cents, if the quantity increases. So the quantity is currently at 85. If we increase it to 86, then we need to increase the price to about 1 over 13. Let's quickly say why the price is going up when the quantity is going up. We're coming from the perspective of the person working, from the retailer. Retailers want to make more money, so they say, if you want me to do more work, you need to pay me more. Luckily, it's only a little bit more to get the increased number of bracelets, but it is the idea, like when you go to work, how do they get you to work more? They say, I'm going to give you a raise. Same thing can happen to a company. So even though we're usually thinking about when price goes down, quantity goes up, it could be the other way around. This is from the supply perspective, whereas if you want somebody to do more, you have to pay them more.